Anyone got zeta value? What is the value for zeta? Anyone?
Sir, 0.4.
Sir, 0.4.
Yes. Tell your roll number.
19CH30018.
And first girl.
19CH10007.
Yeah. Adrija, okay. Anyone else got?
Sir, 0.4.
You tell me how much you got for tau.
Sir, tau is 0.5.
Correct. What's your roll number?
So 19CH10048.
Sayan Maiti. Yes. Good. So I think most of you can do it. Next you go for this. Second one. Determine ultimate value of response and overshoot. Try to solve the second part and let me know the answer.
The ultimate value of the response is 10.
Ultimate value is 10. Correct. What's your number?
So 19CH10009.
Anik Mandal, no?
Yes, sir.
Hmm. Anyone else got ultimate value? Anyone else got this ultimate value of response?
Yes, sir, 10.
How you got?
Sir, I took limit s tends to 0 in y of s into s.
Correct. What's your number?
19CH10007.
Okay. Find now the overshoot.
Sir, overshoot is 0.25, 0.25, I think.
1254.
Yeah, yes, sir, yes, sir.
What's your number?
Sir, 19 says 1,009.
Bardhan?
Yes, sir, I'm still trying, sir. Sir, could you mention how will we find the overshoot? I understood how will we find the response.
Overshoot, the formula we have derived, no? Directly you substitute the values. Just you need zeta value, you see. All expressions we have derived in the last class. We are just going to use now.
Yes, sir, yes.
0.254, sir.
How
Overshoot.
you? What is the formula?
Exponential of minus pi zeta by root over 1 minus zeta square.
Yes.
So that
correct.
part.
Yeah. What's your number?
18CH30016.
Correct. Now you find the rise time. Third question is calculate the rise time. Rahul Kumawat. Rahul, can you hear me? Rahul Kumawat. No answer. Sneh Bandhu Singh.
Yes, sir.
Did you get the value for overshoot?
Doing, sir.
Kunja Ravi Kiran.
Rise time will be.
Yes, sir.
I am coming to Vardhan. Yeah, Kunja Ravi Kiran. What did you get the value?
Yes, sir. 1.08. That you told in yesterday class formula. That TR is equal to tau by root over 1 minus zeta square into pi minus tan inverse of root of 1 minus zeta square by zeta.
Perfect. Answer is perfect. What's your roll number?
18CH30016.
Yes. Yeah, Vardhan, what you were saying?
I was about to tell the answer 1.08.
Okay. Correct. Anyone else got the answer?
Yes, sir. 1.08.
See, I am showing the answer now. I think most of you did it. So you fix your target to make the last term in the denominator polynomial 1. Okay, always you try to do it. Last term in the denominator polynomial 1. Okay, then equivalent term we know tau square s square plus 2 zeta tau s plus 1. Accordingly, you can get the values. I repeat, the last term in the denominator polynomial, you try to make 1. And then you compare with the standard transfer function and find all these values, kp, tau, and zeta. Okay. Ultimate value of the response we get by using this final value theorem that is shown here in Laplace domain. You can also use the time domain. In that case, limit t tends to infinity, yt is there. But it is wise to consider this Laplace, the formula in Laplace domain, because transfer function is given in the problem. Overshoot, directly we can use our equation. All the values are already determined. Only one value is there, in fact, that is zeta. And then last question was rise time. That requires the expression of which requires two parameter values. One is tau, another one is zeta. Okay. So next we will start the second order systems. We already know these two types of second order systems. In fact, we discussed 3 types of second order systems. First one is connecting 2 or more first order systems in series. In fact, what I want to say here is that if we connect 2 first order systems, we will have second order dynamics. If we connect 3 first order systems, we will have third order systems or third order dynamics. If we connect 4 first order systems in series, we will have fourth order dynamic response. And second one is, if we include a controller for a first order process, we will have second order process. Another multi-capacity process we discussed, that basically considers the mechanical or fluid element in a process. Okay, that is the elemental part. Basically, we are discussing the process control part. We need the complete process. That's why we are not considering that. Now let us discuss these two types of multi-capacity processes one by one. See, these are the two typical examples of multi-capacity, in fact, second order systems, which include 2 first order systems in series. You draw both these schematic diagrams because we are going to elaborate these two second order systems. Yes. Now you see in the first case, that is non-interacting tanks. First question is why it is called non-interacting. Why the second system is called interacting. Okay, so in the first case you see tank 1 interacts tank 2. Tank 1 interacts tank 2. You can think like this way. If there is any change in H1, H2 gets affected. I repeat, the first system example is called non-interacting system. Reason is tank 1 interacts tank 2. It means if there is any change in H1, H2 gets affected. But if I ask you now, if there is any change in H2, does it affect H1? What's your answer? If there is any change in H1, H2 gets affected. Does it true vice versa?
No, sir, it does not.
No, sir.
It is not. That means it is actually one-way interacting system. Tank 1 interacts tank 2, but it's not true in reverse way. Okay, so this one-way interacting system here is called non-interacting system. Okay, it is basically one-way interacting system, and that is called non-interacting system. So what do you think about the right-hand side system? Tank 1
Yeah.
interacts tank 2. Does
It
it
would
true?
interact, sir.
Which one?
It will interact both in both ways.
Yeah, both ways the tanks are getting interacted. Okay, if there is any change in H1, H2 gets affected. Similarly, or in the reverse way, if there is any change in H2, H1 gets affected. So that's why the right hand side system is basically interacting system. Now let us discuss these two system examples. We'll go first with the first example, that is non-interacting tanks. So what we want to see, our target is we have connected to first order systems in series in both the cases, and we want to investigate the overall transfer function is second order or not. This is our primary goal. Okay, I repeat, two first order systems connected in series. Now we want to investigate whether they are yielding second order transfer function or not. Let's see. We are going to consider first these non-interacting tanks. So for which we need to develop the individual transfer function for tank 1 and tank 2, and then we will find the overall transfer function. I repeat, we need to first develop the model for tank 1, followed by tank 2. Then we will develop the individual transfer function for both the tanks. And finally, we will find the overall transfer function. And we want to check that overall transfer function is second order or not. Let's proceed. See, this is the model equation for tank 1. This is the model equation for tank 1. So we can write in terms of deviation variables, you see. I already mentioned that we can directly write the model equation in terms of deviation variable. For that, you just need to identify the variables and put the prime symbol over those variables. Fine. Now we can rearrange this equation, or we can rewrite this equation in this form. We have written this in terms of time constant and gain Kp. So what is our transfer function? You see, our transfer function is output is H1 and input is Fi. So output by input, that is equal to this Kp1 by tau p1 is plus 1. So for tank 1, this is our transfer function G1, which is obviously the transfer function of a first order lag system. Okay. This is the transfer function for the first tank, and we are expressing it by G1. And this transfer function is nothing but the transfer function of a first order lag system. Can you now determine similarly for tank 2? Do it quickly. Let me know the transfer function for tank 2. You just follow this approach. Find the transfer function for tank 2. I have shown for tank 1. Now you go for tank 2. It is quite similar.
Sir, it will be the same, like it will be A2R2 by A2R2S plus 1.
What is Kp2?
KP2 मतलब KP2 will be R2 and then tau P2 will be A to R2.
Yeah, correct. What's your number?
19CS30018.
Yes. Anyone else got?
Yes, sir.
Same expression you got?
Yes, sir. Kp upon tau P2 S plus 1 and Kp2 is R2 and tau P2 is A2 into R2.
Yeah. Now verify. I'm showing now for tank 2. Fine. So what should be the overall transfer function? Tell me what should be the output, what should be the input in the overall transfer function. Overall means we are just considering both the tanks. Can anyone tell what should be the overall transfer function for both the tanks?
Sir, Kp2 divided by tau P1S plus 1 into tau P2S plus 1.
Oh, great. What's your number?
The 19 says 10009.
So what is the input? What is the output for overall transfer function?
Sir, the input would be like it is the output would be H2S. I mean H2S inverse, and the input will be FIS.
See, now I am showing. If you consider both the first order tanks or liquid tank systems, in that case our output is H2 and input is Fi. You can revisit the schematic diagram. If we consider the entire system or both the tanks, in that case our output is H2 and input is Fi. To see this, you can revisit the schematic diagram. Then it is straightforward to rearrange the transfer function and get the final form. Okay. So what is your conclusion on the overall transfer function? Are we getting second order transfer function? I mentioned at the beginning, no, our goal is to find the overall transfer function and that should be second order. You see, it is second order. So it is at least proved through the example that if we connect the two first order systems in series, the overall response is second order response. It is proved. Now, if we take the inverse of Laplace transform of this equation, this one, H2 prime by Fi prime equal to Kp2 divided by tau P1 is plus 1, this form, we get this expression. Final expression I am giving you directly. If we take the inverse of Laplace transform, we get in time domain this expression. Final expression you see. Okay. Now you come to the remarks. As I told, connecting to first order system aids second order system. It is quite obvious from the overall transfer function. Our first remark is, if we connect to first order systems in series, we get second order system. It is proved through the derivation of overall transfer function 0. Now overdamped response of overdamped system is a Sept. It's a sigmoidal shift. It means there is a slow change at the beginning and then it picks up the speed. Response of overdamped system is a Sept, that is sigmoidal shift. Initially it changes slowly, then it picks up the speed. I'll show you graphically how it looks like. And in converse, for the first order system, the response is faster at the beginning. Okay, so let us come to see graphically how it happens. You draw this picture. First order response we already got before, and other blue color responses are included here additionally. Response of first order system we got previously, from which we have calculated 63.2% on t equal to tau p. I think you can recall this red color plot. For the first order system, when t equal to tau p, we got 63.2% response. So this is that plot only. I mean that curve, this one, red curve. Rest 3 we are additionally including here. Can we draw any conclusion based on this plot? Anyone? Any conclusion from this plot? Student, anyone can add any remark based on this plot? In fact, comparing the 4 curves. You are understanding their A-Sept. Fine, that's why I have mentioned before. A-Sept plot, sigmoidal plot. Tell me any conclusion.
So the more number of tanks in series, the longer it takes to respond to any change.
Yes, it's correct. That means number of capacities if increases in series, then we have delay in the initial response, or delay in the initial response becomes more pronounced, more prominent. Okay, so this is 2 non-interacting tanks. This is 4 non-interacting tank. You see, for the 4 non-interacting case, we are having a sluggish response, particularly the delay at the beginning. Not at the beginning everywhere, you see. Yeah, in fact, at the beginning, we have delayed response. This is one comment we can make, which is written as third point, you see. As the number of capacities in series increases. The delay in the initial response becomes more pronounced. And what do you think? If we compare, you see, the second non-interacting tank and second interacting tank, can we extract another remark? I repeat, if you compare two non-interacting tanks and two interacting tanks, we are having different response. Can we extract any additional remark? Anyone? Comparing the response of two non-interacting tanks and two interacting tanks, can we extract any remark? Vardhan?
Yes, sir. Like
one case is two non-interacting tank. In another case, we have two interacting tank. We are having different response. We cannot extract a remark, additional remark.
The interacting tanks reach the ultimate response faster. Sorry, I mean the non-interacting tanks.
Yes. So we can say that the interaction basically makes the response sluggish, isn't it?
Yes.
Interaction makes the response sluggish. So this remark also we can add. Interaction makes the response sluggish. And this is the final case. We have considered two first order tanks in series, but we may have n number of tanks in series. We have considered a case where two first order tanks in series, but we can have total n number of tanks connected in series. And if that is the case, our overall transfer function becomes like this. For n number of tanks connected in series, we have this overall transfer function. Agree? So do you have any question on this for the non-interacting case? Do you have any question? No. If not, let me ask one question. For the two tank system, we got this overall transfer function. Now question is, so this is what type of response basically? I mean, it's the overall overdamped system or underdamped system response? I repeat my question. We have considered two non-interacting tanks connected in series. So we got second order overall response. Question is, there are three types of second order response: overdamped, underdamped, and critically damped. So this falls under which category?
So overdamped.
I mean, how you were saying, or at
Previously you had showed us.
oh, this is not the reason. No, you give the reason. Or at what condition it is overdamped? Why it is overdamped and at what condition it is overdamped? Anyone? So can you tell in which case we have overdamped? I mean, how we can define
zeta greater than 1.
any other way we can define? Zeta greater than 1, that is one case. Any other way?
Sir, is it regarding poles?
Yes.
Sir, P1 plus P2 greater than 2.
What about the poles?
If they're distinct and real.
Is there any scope to get distinct and real poles?
I think yes, sir.
You see the overall transfer function and you try to match with your comment.
Sir, P1 plus P2 should be greater than 2 to get zeta greater than 1.
Yeah, straightforward way you try to get that. What issue you were saying that we will discuss.
So expression of zeta is tau p1 plus tau p2 by 2 into under root tau p1 tau p2. So it is arithmetic mean of tau p1 divided by geometric mean of tau p2. And from AMGM inequality, we can say that numerator is always greater than denominator.
Yes. So it is overdamped response, fine?
Yes, sir.
And you want to add any provision, I mean condition, at which condition it is overdamped?
Sir, it will always be overdamped because numerator will always be negative.
Let me put the question like this way. Why it is not critically damped?
Sir, when P1 and P2 will not be equal to 1.
Yes.
Yes.
You just add this one. Okay, tau p1 and tau p2, if they are equal, then it is critically damped. Okay, if they're not equal, it is overdamped. Correct. Okay, so I think we cannot proceed to the next topic because we have only 5 minutes time. In the next day, we'll discuss this interacting tank system. Okay, and we want to follow the similar approach. And our goal is also to find the transfer function, overall transfer function, and investigate that the overall transfer function is second order transfer function. Okay, that is the goal. Like non-interacting tank systems, our goal was to find the overall transfer function and to inspect whether it is second order or not. The same thing we will follow for this case as well. For the interacting tank also, we'll try to find the overall transfer function and see whether it is second order or not. Okay, I think we do not have time to complete this topic, so we'll do in the next class. Okay, thank you then.
Thank you, sir.
Thank you, sir.
Thank you to everyone.
Thank you, sir.